Hey everybody, Mr. Murray here. You thought you had a couple weeks off from the sound of my voice, but sorry to disappoint you. I'm going to try to move forward with this a little bit. I hope everybody is doing okay, and of course, feel free to reach out to me, via email with any questions you have with this stuff. So we're going to try to take a look at this particular kind of word problem, which comes up with differential equations. Focusing in on the phrase directly proportional. You may recall from Algebra 1, Algebra 2, that when two things vary directly or have a direct proportional relationship, that means they are related by y equals k times x, where k is just some constant. In Algebra 1, it was really just the slope of a line with a y-intercept of 0, which is why you probably encountered it back then. But we're going to take a look at it in differential equations today. So we have v of t, which represents the population of computer virus, is increasing at a rate directly proportional to this quantity, 800 minus v of t, where the constant of proportionality is k. And so the key is first breaking this down. Since they didn't set it up for us, let's translate this into calculus terms here. V of t is increasing. So similar to related rates when we saw that kind of phrase, that's discussing the rate of change of v of t, or dv dt is increasing at a rate directly proportional, so by some constant multiplied by this quantity, 800, minus v of t. And at this point, we can really, ditch the v of t and just call it v, if you like. Note that the two variables in this problem are v and t, population of the virus in terms of t. K is a constant, which we're going to find at some point. And of course, they've given us this initial condition, v of 0 is 500. So to find v, given the differential equation, we're going to solve by integrating. But of course, we have to separate those variables first, like we've been doing lately. So I'm going to divide both sides by this quantity, 800 minus v, to get it over on this side with the dv. 1 over 800 minus v dv. I'm going to multiply both sides by dt, and I'm going to have k dt. Now we've separated the variables. I'm going to integrate here. Antiderivative of 1 over 800 minus v, that's going to be the natural log of the absolute value of 800 minus v. But just be careful because of that constant coefficient of v being -1 there. You would really need to account for that. If you need to use u substitution to do so, fine, let the whole denominator be u, but I think that's a pretty simple thing we've seen that we can account for just by putting a -1 out in front of the whole thing. On this side, of course, just remember k is not a variable, it's representing a constant, so that's no different than if there was a 5 there, and the antiderivative of that with respect to t is going to be k, whatever k is, times t. Plus c, of course. Every time you integrate, you have to account for that constant that could be on the end there. All right, so now it wants us to isolate v to solve for v of t in terms of t and k, so I'm going to do that right now. You could, if you wanted to solve for c, by plugging in this 0.0500, you could do so right now. But I'm going to maneuver a little bit first just so you see another way to do it. I'm going to divide both sides by -1, so ln of 800 minus v is equal to negative kt minus c. Again, with these constants here, as we've been talking about lately, you can continue the algebra operation to them and call them negative k and negative c, but it's still just a constant. So if you'd rather, you could just continue to call that plus c and plus k, because whether k is positive or negative, that's going to bear out in the math in a few minutes anyway. If you wanted to distinguish and say, well, really now it's a new constant than it was right here, you could call it c2, k2, whatever you like. I'm just going to call it k and c for right now. Getting rid of this log here, we're going to raise e to each side, and that's going to allow us to get rid of that log on the left side. We'll have 800 minus v is equal to e to the kt plus c. That's all in the exponent there. And now we're going to do that little maneuver which we've been doing a lot lately. Some may not have been doing it. And again, you still don't have to, but in these particular problems is why I like to do it. This, just to refresh you on where this move comes from, it's breaking up that exponent with that sum into e to the kt times e to the c. And e to the c is just a constant raised to a constant, so that's just a new big constant. So I could just call that whole thing another c or q or a or just any letter you want, as long as you realize it's a constant. I'll call it c2, e to the kt. So right now we've got two constants going on that are unknown, k and c, or c2, or whatever you're calling this coefficient. Now I said we had to solve for v of t in terms of t and k. T and k are fine, but we've got to solve for c, and that's why they gave us that initial condition of 0, 500. If you want to isolate v first, that's fine also. If you want to just plug in the point, fine. I'm going to plug in 0, 500 right now. So that would be 800 minus 500. 500 represents the population that have this computer virus. Maybe I should have changed it to coronavirus to keep it a little more topical. And 0 is the time. So k times 0 is of course still 0, and that's just e to the 0, which is 1. So we have that c2 is equal to 300. And that's why often it's nice in these problems to have that extra move where you've sort of renamed that constant as this coefficient, because a lot of times you'll be plugging in 0 and you'll just get 1 times that constant you're after, and it's kind of already isolated, as opposed to like being in an exponent where you've got to take the log of each side or anything like that. So we found this c, which means now 800 minus v, the last place where I plugged in was this. 800 minus v is 300 times e to the kt, and we can solve for v by adding that, subtracting this, and you'll be left with 800 minus 300 e to the kt. Oh, got a little off the screen there, but that's what keeps this movie edgy. It's the low budget aspect, right? All right, so don't judge my editing or my pacing, John Lee. I'll get there someday. Okay, now moving along, part B here. We have v of 2 is 700. That's going to allow us to find k. If you got two constants, then you need 2 points to help you find them. It's a basic systems of equations kind of thing. So I've already found c, but now I'm going to find k. So going back to this equation I just found, in that last step, I'm going to plug in 700 for v and 2 for t. And so you're going to have e to the 2k. Subtract 800 from each side, you'll have negative 100 equals negative 300 e to the 2k. Divide both sides by negative 300, you'll have positive 1/3 is equal to e to the 2k. And now to solve for that k, we're going to take the natural log of each side. So ln of 1/3 equals ln of e to the 2k. It's just 2k, of course. So now we're going to divide that by 2. The ln of 1/3 is fine to leave it that way. If you would rather call that, sometimes people would rather call that negative ln of 3. That way you're not rewriting a fraction each time, on the inside, if that can get a little awkward. Whatever, it's all good. Then we're going to divide by 2. So k is equal to negative ln of 3 over 2, or negative 1/2 ln of 3. Or again, ln of 1/3 divided by 2, or if you want to further play around and make that 1/2 an exponent, it'd be ln of the square root of 1/3, raising the 1/3 to the 1/2 power. So I think we're good right there. That's at least one version of k that we're fine with. And now that we know c and k, they're asking us part c. Let's find the limit of this function as t approaches infinity. So we've got v of t now in full. V of t, or v, is equal to 800 minus e, so minus 300 times e to the k, and k is now negative ln of 3 over 2, all times t. That's all just a big constant coefficient of t. Just be careful that t is not on the inside of the log or anything. And we're trying to find the limit of this as t approaches infinity. So remember, the basic idea of a limit as t approaches infinity is, maybe you're thinking, does this graph level off? Does it have an HA? Does it take off to infinity or negative infinity? And you're basically just trying to imagine what happens to the value of this as t, in this case, gets infinitely large, as time goes on. So I think it's easy just to think about what's happening to this. If you plug in a really big number, 100, 1,000, a million, a trillion, and then you're multiplying it by negative ln of 3 over 2. Now ln of 3 is a positive quantity, so when you have the negative out in front, that's a negative quantity divided by 2. So this is a negative number, this constant. And if you had called it ln of 1/3, how many of you would have realized that ln of 1/3 is actually a negative number? Because you're saying e to what power gives you 1/3, and that's 1/3 is less than 1, so it takes a negative exponent to do that. So this is a negative number being multiplied by, say, 1,000,000 years. Then you're going to get an extraordinarily small, or big negative, if you want to call it that. And e to like the negative millionth is 1 over e to the millionth, or is practically getting to be 0. It's getting infinitely close to 0. And so 0 times this is going to give you 0. So you're basically going to be doing 800 minus a negligible amount, practically 0. And so you're going to get 800 is the answer to that. So the limit does exist. And if you want to approach it from a graphical standpoint, you could, depending on how well you remember your Algebra 2, your pre-calc, this kind of graph, this exponential graph, it's got a base of e, which is bigger than 1, so you'd be dealing with sort of an exponential growth initially, but then you'd have a negative coefficient in front of the exponent, causing a reflection over the y-axis, which is making it be an exponential decay. Then this negative coefficient out in front of the base is a reflection over the x-axis, making it look like that. And then with the positive 800 being added to it, it's shifting it all up 800 units, meaning that's our HA, is y equals 800, and you've got the graph looking like this, where its initial amount is 0, 500, as they gave us in the problem. But as you move on, as time goes on, you're getting infinitely close to that HA, which is y equals 800. So that is our limit. Okay, email me if you have any questions. Try the problem on page 2. I'm going to post the solutions online, and we'll keep doing our best here. So good luck, everybody. Hope everything's good, and be well.